Hello, my name is Carolyn Otten, and today I'll be discussing analytical approaches for solving food and beverage challenges. Carolyn J. Otten has over 15 years of experience in directing and performing analytical chemistry investigations. Dr. Otten has served as a scientific technical consultant and expert witness, providing testimony for cases involving product liability and patent infringement. She has designed and supervised numerous projects involving food investigations, including off-odors, contaminants, and ingredient claims. Skilled in communicating results to clients, she is responsible for technical accuracy and data quality. Food and beverage manufacturers face multiple challenges, from demands for convenient yet safe packaging to concerns over harmful chemical contamination. Despite rigorous quality standards and testing programs, how can food and beverage manufacturers confront these problems? Today, I will discuss a strategic approach to meet these tough challenges. Here are some examples of specific challenges facing the food and beverage industry. First, we'll discuss the misunderstanding of the word chemical for the general public and how it can be manipulated to generate fear. Next, innovative packaging systems to allow for convenience cooking. Is it safe for consumers? Does it protect product shelf life and integrity? Next, we'll discuss contamination issues stemming from manufacturing processes. Also, we'll discuss ingredient incompatibility. In other words, the unintended byproducts produced from chemical reaction of ingredients in a new product. And finally, we'll discuss product label claims of being free of certain chemicals. In other words, you might have heard of the term BPA-free, phthalate-free, or fill-in-the-blank chemical-free. You might have seen that at stores on your favorite products. What does that mean? First, let's talk about chemicals. I know that when you hear the word chemicals, it probably evokes a certain emotional response in your mind, and that is by design. I'm, of course, a chemistry person by training, and so when I hear the term chemicals, it actually produces a positive response because I know that we'll be talking about chemistry, which is what I love. But that's not necessarily true for the general public, so let's have a frank discussion about what it means. First of all, chemicals are essential building blocks for everything in the world. All living matter, including humans, animals, plants, are made up of chemicals. All food is made up of chemicals. So whether or not a chemical is good or bad really depends on its specific toxicological properties. A chemical can be naturally occurring or synthetic, man-made, but whether it's one or the other doesn't necessarily mean that it's good or bad. Not all naturally occurring chemicals are good. Not all synthetic chemicals are bad. Here are some headlines that we took from the media that uses the term chemicals. The first one comes from CNN, and it's pretty general. It talks about 7 other chemicals in your food, which if you think about what we just talked about, how all food is made up of chemicals, I'm not really sure what you're supposed to take from this headline. The next is a headline from the New York Times where it says, "Chemicals in food may harm children," pediatricians group says. Again, we just talked about chemicals and how all food is made up of chemicals. And so although it's generally telling you that they're going to be talking about certain chemicals in food that may harm, it doesn't really give any specific information about that. The next headline is from The Guardian earlier this year, and I actually like this headline particularly due to the punctuation in it. It says, "Modern myths about cancer, from chemicals," and they have that in single quotes, "to food to Wi-Fi." And I like the fact that they put chemicals because it's sort of conveying that when you see or hear that word, it's supposed to mean something. And as we just discussed, the term chemicals is very general, and you can't really tell anything about a specific chemical unless you identify that chemical. Food and beverage companies are constantly dealing with the launch of new, innovative products. The following are examples of innovative packaging systems that may require investigative analytical testing. First of all, let's talk about microwave steam-in-the-bag technology. These have been designed for starting out things like vegetables, and they have kind of evolved over time. And now you see microwave steam in the bags that encompass cream and butter sauces. And even the more sophisticated types incorporate meat and pasta. And so what you need to think about with these packaging systems are, as the food inside these packages gets more sophisticated and more complex, is the same packaging system sufficient in order to meet both the needs of the consumer in terms of convenience, how it cooks, how it tastes, and in terms of safety? Next, we'll talk about the crisping sleeve that was designed to heat the insides of certain food but allow a crispy crust. Now, these types of materials are very interesting technologically because they have been designed to incorporate different materials that would allow cooking at different temperatures. And so with the complexity of these types of packaging systems, you are often incorporating different materials that may not often be in contact with one another. And you also have to consider what happens when they come into contact with food. Next, microwave popcorn. This is definitely a technology that everybody has been exposed to, and it's gotten more sophisticated over the years, particularly having to do with all of the different flavors of popcorn that are now available in a microwave packaging system. And so not all popcorns are the same. If you're going to have different food or different ingredients, those are going to have different chemical properties, and they're going to interact differently with the packaging system. So things like jalapeno, white cheddar, kettle corn, all of these have different ingredients in them. They have different chemical properties, and so I'm sure different considerations have gone into the packaging system depending on the type of food or the type of flavor that has been developed to be cooked inside it. And finally, something that we've probably all been exposed to over the past few years are single-serving coffee pods. These are interesting because they are officially licensed beverages designed for use in a specific manufacturer's hot beverage dispensers. And what's interesting about them is not just the fact that they have served as a packaging container, but in the design, they have been designed to discourage the use of off-brand or generics. So there's a certain type of technology in some of these coffee pods that has been placed in these packaging systems that is supposed to encourage that specific manufacturers will work in certain coffee machines and disallow them to work in others. Now I'm going to give some examples of some mainstream food and beverage issues that you've likely heard about over the past 10 years. The first one I'm going to talk about is benzene formation in beverages. Benzene, of course, is a known carcinogen, and here's an image of its chemical structure. The FDA first became aware that benzene was present in some soft drinks back in the 1990s. At that time, the soft drink industry informed the agency that the benzene could form at low levels in some beverages that contained both benzoate salts and vitamin C, or ascorbic acid. The FDA and the beverage industry engaged in research in order to identify certain factors that contributed to benzene formation. So these would be elevated temperature, light, and certain metallic ions that may be present in the packaging systems, the cans, for these beverages that could catalyze the formation of the benzene. An example of this would be you had this type of beverage sitting in your car, so that would be experiencing elevated temperatures. Probably would not be exposed to light, but it may be exposed to metallic ions due to the can. So after years of investigation, this resulted in some manufacturers reformulating their product in order to reduce the propensity for benzene formation. However, in 2005 and 2006, there became reports that benzene had been detected at low levels in certain types of soft drinks and other types of beverages, such as energy drinks. And so this initiated a study, and in this study, the FDA tested almost 200 products, and of those over 200 products, about 10 of them had levels of benzene that exceeded 5 parts per billion, which is the standard limit set for water. The next mainstream food and beverage issue that I'm going to discuss is melamine in baby formula or pet food. So what is melamine? Melamine is an industrial chemical, and it can react in order to form cyanuric acid. So here's a chemical structure of melamine on the left and cyanuric acid on the right. And what may be significant if you take a look at the chemical structures is you can see that there's a large amount of nitrogen in these structures, which is important for why it was actually used in these types of products. So combinations of melamine, cyanuric acid can lead to problems like kidney stones and other renal problems in infants, young children, and pets. So basically, how do these components get into the food? Well, they're actually added on purpose. So these represent chemical adulterants, and the reason that they are added is not because they have any beneficial, but they represent components that actually have a high nitrogen content, and they were added for the purposes of basically serving as a kind of an inert filler for cost savings, often by overseas manufacturers. So the thing that both pet food and infant formula share in common is that they're high in protein. Of course, protein is composed of amino acids, and amino acids are high in nitrogen. And so kind of the thought process is if they're looking to try to save money, if they add in some melamine, this would actually serve as a component with a high nitrogen content. And when certain analytical testing is done from a QC perspective, they're not necessarily testing for very specific components, but they might be doing more of a general screening test, looking for a certain percent nitrogen content that one would expect from a product like pet food or infant formula, which is high protein. The past two slides were examples of small molecule contaminants that were identified in food and beverage products and have been tested both in our analytical labs and others. However, different analytical labs do different type of testing. Here's a list of some of the services we offer at EAG. Off color, off odor, off flavors, contaminant identification, packaging migration studies, competitive packaging, reverse engineering, liability, personal injury related to contamination of food or beverages. In 2017, EAG became part of Eurofins, which also performs food testing. For a comprehensive list of their service offerings, here's a link that you can click on. But other analytical tests that are being performed by Eurofins are microbiological testing, nutritional labeling testing, allergen testing, GMO, probiotic identification, fats and oils, dairy, meat species identification, fish authenticity, and other types of testing. The first case study I'd like to discuss is BPA in drinking containers. So BPA, what is it? BPA stands for bisphenol A. And here is a chemical structure of what BPA actually looks like. So BPA is an industrial chemical used for making specific plastics, such as polycarbonate, and resins, such as epoxies. Commonly found in reusable water bottles and inside the liners of metal cans used for food storage. Basically, the uses of all substances that migrate from packaging into the food, including BPA, are subject to pre-market approval by the FDA as an indirect food additive or food contact substance. The FDA regulations for BPA date back to the 1960s. So the term BPA-free is a term that you often see on labels or stickers, or you see it all the time these days when you're going shopping for different products. So we decided to take on our own study to look at different drinking containers. Some of them, they wouldn't have any labels on them, so we were curious to see whether or not they contained BPA, and some of them actually did have little stickers on them that said BPA-free. We were also curious to know, did we detect any of those that are claiming to be BPA-free in those actual drinking containers? And so we set out, went to the store, obtained some different test samples. The first one was a white water bottle labeled BPA-free. The second one was a red water bottle. The third, a green water bottle, which was labeled BPA-free. The next one, a pink water bottle, also labeled BPA-free. And then we decided, as long as we were doing the experiment, we would also extract some different cans, since the liners for certain cans can also contain BPA. So we tested a sparkling water aluminum can, and then also a diet soda name brand type beverage, which was also an aluminum can. So we sampled from these materials. We cut up these materials into small pieces, and then we performed a solvent extraction in order to extract out the BPA from these different materials. So here's a photographic image of some of our extractions. So basically, samples were prepared following an in-house solvent extraction method. 1 gram of sample was extracted in about 5 grams of solvent at elevated temperatures on an orbital shaker for 2 hours. The samples were centrifuged, filtered, and then the supernatant analyzed alongside a bisphenol A standard using an HPLC fluorescence detection method. So if you're not familiar with chromatography, let me give you a one-slide primer. Basically, in this term, chromatography means separation. So when you're doing a solvent extraction with the hope of extracting out a certain component or analyte from a material for identification and quantitation, often whatever solvent you choose is not just going to extract out that one component. It's going to extract out a mixture of components. And in order to accurately identify and quantify an analyte of interest, you need to have an analytical method that has a separation step, and this would be a chromatographic method. So components and mixtures are separated based on differences in their affinities for what's called a stationary phase, and that's usually a solid material that your column is packed with, and the mobile phase. And what the mobile phase is depends on the type of chromatography, but it could be a liquid phase or a gas phase. Components are detected and measured as they elute or move through and come out of the column and are detected by a detector. The time that a component spends in the column from the injection until the detection is called the retention time, and it's an indicator of the component identity based on the chemical affiliation for whatever the molecule is, how chemically similar it is to the stationary phase. If it's chemically similar, it's going to want to remain among the stationary phase, and it will take longer to elute from the end of the column. If it's chemically different, it will not want to remain with the stationary phase, and it will tend to come out sooner. So here we're actually able to take a look at the data, and in this case the data is called a chromatogram. The very top chromatogram represents a method blank. So that's basically any type of solvent or activity that was done in the extraction or the sample preparation is done, and we create a method blank. Only no material is actually extracted. So any type of potential contaminant or artifact of the sample prep, we run a method blank just to make sure that there isn't anything that could be giving us a false positive. The next chromatogram is a BPA standard. That's where we purchase an analytical standard of bisphenol A, basically in order to understand where it shows up in the chromatogram. And then also for quantitation purposes, we use that to calibrate the instrument. In other words, we prepare a sample of known concentration and we measure its response. Therefore, when we're actually testing unknown samples, if we do get a response, we are then able to compare it back to the standard and solve for the unknown concentration based on the known response of the standard. So here are a couple of chromatograms. The first one is the white water bottle that was labeled BPA-free. The next chromatogram is a red water bottle. Continuing on, looking at the different chromatograms, again we have the BPA standard up top, and then we have the next 4 samples. The green water bottle that was labeled BPA-free, the pink water bottle, which was also labeled BPA-free. Both of them have peaks that are fairly consistent with the BPA standard. Then we have the sparkling water aluminum can and the diet soda name brand aluminum can. Both of those also have peaks that have consistent retention times with BPA. If you actually looked at the specific retention time, the apex of these peaks, they might be a little shifted from the actual bisphenol A standard. And the way to address whether or not these peaks are actually BPA, or could it be another component that has a chemically similar structure to that, we would perform a spiking experiment where we spike in a known amount of BPA into these sample extracts. And basically, if we see the peak basically increase in intensity, that would be confirmation that the peak that we're seeing, even if it's slightly shifted a little to the right or left of the standard, would be due to BPA. And if we actually see a shoulder or a dual peak, that would suggest that the peak that we thought might be BPA actually is from a different component because it has a slightly different retention time. So here is a summary of the results from our experiment extracting out different materials used in drinking containers. The white water bottle that was labeled BPA-free basically was a non-detect. So was the red water bottle. Now, would we ever be in a situation where we would, as an analytical lab, produce results that would say there is 0 BPA or no BPA? The answer is no. For any type of analytical method, you're going to have a certain limit of quantitation and a limit of detection. And that's basically, at a certain level, the instrument loses sensitivity to be able to detect down to extremely trace levels of components. And a limit of detection is very specific, both for the analyte, the matrix, and the analytical method. And so basically, in this case, we would probably not express this as BPA-free, but we would say that BPA was not detected. And we could say it was not detected and provide a certain limit of detection. The next 4 samples, we actually did detect BPA, and we created a calibration curve and used that in order to quantify the levels of BPA in the samples. And then this is calculated back to the mass of the individual sample. And so the green and the pink water that were labeled BPA-free both had about 0.005% level of BPA. And then both of the sparkling water can and the diet soda name brand aluminum can, those also had similar order of magnitudes of BPA that were quantified in those products. The second case study I'm going to discuss is monosodium glutamate, or MSG, in soy sauce. A little about monosodium glutamate, or MSG. What is MSG? Basically, it is the sodium salt of a non-essential amino acid called glutamic acid. And when you actually make the salt form, it is basically the sodium salt of glutamic acid. MSG is used as a flavor enhancer to savory foods, but MSG alone doesn't have a pleasant taste. So this non-essential amino acid, glutamic acid, is actually found naturally in many foods, such as tomatoes, cheeses, yeast, and different soy extracts. It's currently produced from bacterial fermentation. MSG is generally recognized as safe by the US FDA, but it does have a negative reputation among the general population. The popular belief is that MSG causes headaches and/or sleepiness, but there's not a whole lot of data that actually backs up this claim. So before we talk about MSG and soy sauce, I think it's important to have a little bit of background about MSG and different food requirements. So in terms of the FDA requirements, food that contain added MSG need to list MSG in the ingredient panel on the packaging. Foods with ingredients that contain natural MSG need to be listed on the ingredient panel, but they don't have to specifically call out MSG. They just need to list the ingredient that would contain natural MSG. However, foods with any ingredients that naturally contain MSG can't claim no MSG or no added MSG on their packaging. MSG also can't be listed under the general term spices and flavorings. So, considering all of these factors, the inherent issue with performing a study or a quantitation of MSG in soy sauce is that there's the naturally occurring MSG, and then there's the added MSG. And basically, naturally occurring glutamate or glutamic acid is chemically indistinguishable from any added MSG in those products. Fermentation process of soy protein affords primary amino acids, and thus when you're doing a quantitation, the quantitation will be for total glutamate, and that would be the sum of any naturally occurring glutamate and any added glutamate. So on to our chemical analysis. With some analytes, your analytical method can detect the molecule as it is. However, with certain analytes, they're not strong responders, and they must be chemically derivatized in order to be detected at low level. Here is the specific derivatization scheme that we use for detecting MSG in our study. So here's the chemical reaction. We have phthaldialdehyde reacts with mercaptopropanoic acid, and in this case, our primary amino acid is the salt monosodium glutamate. They react together. Basically, this forms a fluorescent adduct of MSG. Then acetic acid is injected onto the autosampler to quench the reaction. And so, although you could perform this on the benchtop in a round bottom flask, we actually developed a method where you actually can set up all the reagents in different HPLC vials, and basically on the HPLC autosampler you can get the reactants injected into a single vial and have the chemical reaction basically happen in the HPLC vial. So you're not having to work up the reaction and then put it on the HPLC. So this derivatized amino acid with this fluorescent tag is then the component that's actually being detected, and that would allow us to both identify and quantify this in different matrices. Over the course of the summer, we collected 6 different soy sauces to compare to one another and to also potentially quantify the MSG present for our study. The very top chromatogram represents our MSG standard that has also undergone derivatization and is being detected by our method. The middle chromatogram represents our soy sauce number 1. And if you take a look at the chromatogram, you can actually see there are many different peaks, and those might represent different amino acids that have also reacted with the derivatizing agent. But for this study, they're not of interest. The very bottom chromatogram represents our soy sauce number 1 that we've actually spiked with a known amount of MSG. And the spiking study we discussed in our previous case study is basically to confirm, is the peak that we're calling the derivatized MSG actually that? And if you spike in a known amount and you actually see 2 peaks, that would be confirmation that the peak that you thought was your analyte of interest might actually be something different. In this case, we actually see only 1 peak. The reason that it's actually a lower intensity than soy sauce number 1 just has to do with the fact that when we're performing the spiking study, in order to keep the level of the analyte in a specific range that can be used for quantitation, we often dilute the spike more such that it can accommodate additional analyte in there, such that it remains within the linear range of our calibration curve. So this next slide is just a stacked comparison of soy sauce 1, 2, and 3. And the peak of interest that corresponds with the derivatized form of MSG is boxed in red. And as you can see, if you're looking at the different chromatograms, it's interesting to see that even though they're different manufacturers of soy sauce and they do contain different ingredients, that a lot of the peaks, even if we don't necessarily know what they are at the time, they look to be fairly consistent among the different brands and manufacturers of soy sauce. So here are stat chromatograms of the next 3 soy sauces, soy sauce 4, soy sauce 5, and soy sauce 6. And just kind of continuing on with that comparison from the previous slide, what's interesting about this comparison is that soy sauce 4, there are actually much less peaks present in this chromatogram, which may indicate a difference in the ingredients. And so when we get to the slide that actually has the ingredients, we should take a look and see how that soy sauce differs from the others. But they all have a peak that is consistent with MSG. And so these peaks were used and compared to the MSG standard and were used in order to quantify the levels in these different soy sauces. So now we list the different soy sauces and provide the list of ingredients from the back of the packages. And it's interesting to both compare the ingredients and also look at the quantitation results of MSG that we determined in our case study. So those are summarized on the right in the table. They range from the lowest at 0.2% glutamate to the highest at 2.04% glutamate. And first of all, one of the things that we found interesting was when we were comparing the different chromatograms, we noted that many of the chromatograms, even if we didn't know what the extra peaks were, they looked similar to one another. But the one that stood out was soy sauce number 4. And that actually makes sense if you actually consider its ingredient list. That was the one quote-unquote soy sauce where there was actually no soy listed as part of its ingredients. It does list MSG, and because there was no natural source of MSG, they would need to list it specifically in their ingredients, and they do. The other thing that's interesting is that if you look at the different levels, there's definitely variability. But if you were just looking at the back of the packaging, and if for whatever reason you were trying to minimize the amount of MSG, you wouldn't necessarily be able to predict it looking at the ingredients. Because what's interesting is that soy sauce number 4, which actually has no natural soy present, and so no natural source of natural MSG, it actually is representing the lowest amount of glutamate present at 0.2%. And then the other sample that represents the highest amount of glutamate is soy sauce number 6. And it actually lists soy sauce, not just soy derivative or soybeans, but it lists soy sauce as part of ingredient in its soy sauce, in addition to many other ingredients. And it also includes an added monosodium glutamate in that list. So that may be the reason that it actually has the highest amount, because it has 2 different sources of the MSG. One naturally derived from the soy sauce, and then added MSG. Now, you may ask, if there is a natural source of MSG, is there really a reason for them to be adding MSG to that? I don't know. This concludes our case studies for this webinar. So just to summarize, analytical chemistry is a valuable tool to address challenges in a variety of industries, including the food and beverage industry. Depending on the type of investigation and the molecules involved, different experiments can be designed and customized in order to address specific client challenges. Sometimes the need for testing is reactive, responding to a customer complaint or addressing a contamination issue. However, requests are also proactive as part of a quality control program to support marketing claims, to evaluate competitive packaging, or to minimize risk of contamination or prevent a recall from ever occurring. If you ever have a food and beverage related challenge that you are unsure about how to approach, please call one of our technical specialists and they can determine an analytical approach or provide a referral. This concludes today's food and beverage webinar. Thank you very much for your attention. And again, if you have any questions or if you'd like to discuss a project, please feel free to email me at cjotten@eag.com, or you can log on to the EAG or Eurofins website. Thank you for your attention.